kernel density estimation, which is a non-parametric method. We use Gaussian kernels to estimate the desired PDFs in the implementation. So since I'm running out of time, I want to go to the experiments. So we instrumented several programs selected from the open source GNU co-utils, GFutils, and grep. So the performance measure that we presented is S equals W1 is a weight W1 times a log of TPR plus 1 minus W2 times log of FPR plus 1 minus W3 times log of N, where N is the number of states of an abstract transition system. Essentially what it says is that a good performance requires a high true positive rate, a low, so I'm going to reward a program analyzer if it has a high true positive rate. I'm going to penalize the program analyzer if it has a high false positive rate. And I'm going to penalize a program analyzer if it has too many states, if the abstract transition system has too many states. So that's the basic idea. So an ideal program analyzer should have a high true positive rate, a low false positive rate, and should not have too many states. So similar to the rock plot, we plot the performance of a program analyzer with respect to the hyperparameters beta and epsilon. And you can see at the blue point, the purple point, where the optimal operating point optimal operating point is obtained. This is the ideal abstraction, after which you can see a sharp drop in performance. So the left, the y-axis is the performance measure, which is just S. So S is like S has this. The purple point is where S is optimal, after which the performance drops off. So finally, I want to conclude the talk by saying that we introduced a new paradigm of automated program analysis based on empirical abstraction that can be created without full understanding of the intricacies of the whole program under analysis. We have quantitatively characterized the behavior of the program analyzer in terms of true positive and false positive rates, and have provided hyperparameters beta and epsilon that can be tuned to obtain an ideal abstraction suitable to solve a program analysis problem. We also introduced a new idea of representing sets of states of a program using a probability density function. Thank you.
All right. Thank you, Supratik, for the talk. So first of all, apologies everyone for the visual glitches. There seems to be a hardware problem. There was a similar problem yesterday during the tutorials. So Anand, if you could switch to your backup machine so that hopefully we can avoid that in the next few talks. All right, we have time for one or two quick questions. All right, maybe let me start, but please just raise your hand or write in the Slack. Supratik, I was wondering, what is the motivation for this logic for using a variation of CTL? Is that mainly because you work with biosimulation, or is there something from the application that motivates this?
I think the biosimulation is a motivation, and essentially you can see that we use CTLK, but K you can vary. You can vary K from anything like you can fix your K, or you can go K equals infinity, means it's full CTL actually. And so you have to fix the so based on the hyperparameters. So if you again change your logic, right? For example, CTL, if you want to change the K, right, you simply tune your hyperparameters. So essentially the notion of biosimulation brought us into the branching domain rather than the linear domain.
All right, there's a question from Roderick.
Yeah, thank you. So if I understood correctly, you tune your algorithm depending on the true positive and false positive rates. But if you're doing verification of systems that you don't know, I don't think you can tune like that, right? So the question is, what do you do then? And do these parameters carry over from one type of program to a different program?
Yes, that's a really interesting question. Yes. I mean, you can essentially do what we do today, what is called self-supervised learning, So if you know certain properties that for example, if the human knows certain properties, right, then you can use a sort of self-supervised learning today, self-supervised learning to basically tune the performance and to tune the performance. So you can start with a number of abstract states, and then if you can say, okay, I know this one for sure, right? And then you can start your performance, and then if you see it's still falling below that, then you can start tuning. So it's the way to go is essentially what we today call self-supervised learning.
All right, thanks very much. I'm afraid we have to move on already. We're already 3 minutes behind schedule. So let's go to the next talk. The next speaker is Benedikt Maderbacher, placement of runtime checks to counteract fault injections.
And Bernd, just so you know, I'm taking over the screen sharing till Anand figures out the issue with his machine. So I'm going to play the video now.
Excellent. Thanks very much.
Hello, I'm Benedikt Maderbacher, and I'm going to present our paper titled Placement of Runtime Checks to Counteract Fault Injections. This is joint work with Anja Kahl and Roderick Blum. Consider a secure program like the snippet shown on the screen, where we execute some stuff based on values. But what happens if an attacker can manipulate our hardware and introduce a bit flip? This might lead to us executing code or outputting values that we are not supposed to do. A standard software countermeasure against such attacks are error detection codes, and they work by adding redundant information that allows us to check the consistency of our data and detect such manipulations. In this talk, we are going to consider AN codes. They work by taking the original data value and multiplying it by a constant a, and therefore increasing the amount of information in them. And we can check for potential manipulations by taking the encoded value modulo a, and if this is not 0, then we know that the manipulation has occurred. So if we take the encoding constant 5 and want to encode the value 3, we get an encoded value of 15. AN codes are arithmetic error detection codes. That means they are homomorphic over arithmetic operations, meaning that we can encode our values once and afterwards compute our whole program without ever decoding the program, because we can directly work with our encoded values. But there is one problem with doing so. This is error masking. So consider this small program we can see here. So we have a value x. We then multiply it by 2, storing this result in y, checking the consistency of y, afterwards computing the value c as 2 times y plus x. So if you again have a constant a is 5, and look at the concrete value is 2, then as there have not been any manipulations, everything is fine and we're happy. But what happens if our attacker is going to manipulate our value x by adding 1 to it? And as we're dealing with arithmetic codes, this is not an XOR operation, but we are actually adding the arithmetic value of 1. And this will then propagate to the variable y, which then has the value of 22. And our check on y is able to detect this and terminate the program or transfer it into a safe mode. So even though there has been a manipulation, nothing bad has happened because we were able to spot the attack. But if we now remove the check in line 3 and only keep the check in the last line, Then the computation continues and computes a manipulated value of 55 for C. And this, as this is a multiple of our encoding constant 5, we are no longer able to detect this. So in this case, our attacker has succeeded in adding a fault into our program, and after some computation, we were no longer able to detect this. And that means that we have to regularly check for these manipulations, because otherwise doing computations with these values can lead to undetectable errors and successful manipulation attempts. Slightly more formally, our correctness condition is that if we have original program P and a protected program P prime, if we inject into P prime up to K faults, then P prime needs to raise an alarm, or the values of P prime still need to match the original values. But adding runtime checks after every instruction is very expensive and will slow down your program. So what we want to achieve in this work is we want to use fewer runtime checks, but we want to still detect all manipulations within our fault model. And to achieve this, we use static verification, and more specifically, we developed a new abstraction technique and specific loop invariants that help to scale our static verification approach. The technique we are using is model checking. So we first start with the original program P. We then introduce the explicit fault locations and compute our abstract program. And this is then given to the model checker, in our case, a CPA checker, which generates a verdict whether our program is secure, so there are enough runtime checks, or if it's unsecure, we get a counterexample. Let's consider our import program from before. Introducing fault injections means for our fault model that whenever a variable is read, there's the potential of adding a new fault. In this case, they are called error location 1 to location 3. And they are chosen non-deterministically, but up to the maximum number of faults allowed by our fault model. For the abstractions, we make use of a property we call error homomorphism. And this allows us to separate the computation on the actual values from the computation on the faults. So for some operations, it holds that when it be computed on values that have potential faults, this is the same as computing it on the original unchanged values and separately computing it only on the faults. And if we have this split into the original value and into the faulted value, it holds that whenever there is an error in the combined value, then this is detectable if we can detect it just in the error value alone. So from this we can derive our abstraction technique, and this works by tracking the values and the errors separately. So on the left you can see the original program, and on the right we have all the error variables. And these compute this exact same program, but we also know that there has not been an error injected in X, so this is initialized with 0. And now we can also throw away all these concrete values because we don't care about them. We can check if our program is secure by just looking at the error values. And this greatly reduces the state space of our model checking problem, because the error values are bounded by our fault model, whereas the concrete values are everything into a 32 or 64-bit values. From this we can then construct the complete program we give to our model checker that consists of the abstract program with the fault value or with the error values. Additionally, we add all the fault locations and bound the weight of all these injected errors by our fault model. And we have to guarantee that all the values are detectable or there has not been any manipulation, because otherwise error masking occurs. And wherever there is a check in our original program, we can afterwards assume that the fault of this on this variable has been 0, because otherwise our program would have terminated. And this annotated and abstracted program is then given to the model checker. The second concept we considered in our paper are loops. So if you look at this simple while loop here, there are two ways we can reduce the amount of runtime checks in this program. One is to not check all the variables that occur in our program, but only some of the variables. And the other technique we use is loop unrolling. So we considered loops that have been unrolled a few times, but the check only occurs every second iteration, for example. And as we have also abstracted away all the concrete values of our program, we replace all the conditionals in our program by non-deterministic choice, and this gives us an over-approximation of the program. So we are no longer able to guarantee that all secure programs are actually detected as secure, but if we detect something as secure, then we can guarantee that it's secure. So we have a non-complete but sound algorithm. Because loops are difficult to scale for a model checker like CPA checker, we also propose our own loop invariants that are based on the idea of tracking the set of all acceptable errors in a variable. Suppose we have a set of these acceptable errors at the beginning of our loop, then we execute our loop, potentially injecting new faults. We still get the same set of acceptable errors at the end, or an alarm is raised in our program. In the paper, we have a more formal definition that also counts how many errors have already been injected, which is important for the formal correctness. But using this loop invariants, we were able to prove programs which have more loop unrollings because we get a more efficient static verification process. In our experiments, we focus on programs with loops, and we want to optimize them in two directions. One is how many variables we have to check, and the other one is how often we have to check them, so how many loop unrollings we can do. We also compare this with two other abstraction levels, one from previous work that counts just the number of errors, and the hybrid approach that actually tracks the values but only considers their Hamming weight when checking them instead of trying to decode. And the first algorithm we looked at is CORDIC for computing sine and cosine values. And in this case, we were able to reduce the number of runtime checks by a factor of 3. And it took less than 1 hour to verify this. And we were only able to do this using our invariants. And the second experiment we looked at is an algorithm to generate Fibonacci numbers. In this case, we were able to speed up the number or to reduce the number of runtime checks by a factor of 10, which took, with our abstraction technique, about 2 minutes to verify. And here we can also see that loops inferred by CPA checker took significantly longer than our invariants, and that we can trade the static verification time against runtime, because the more simpler and more abstract abstraction techniques allow us to faster verify programs, but they also need more runtime checks. So, for example, using the work from abstraction level 3, which is the one presented in previous work, we have to check 2 variables every iteration, and now we only have to check 1 variable every 5 iterations. To conclude this talk, let me summarize shortly. We have proved that programs, or we present a technique to prove programs secure against fault attacks, and we're able to reduce the number of runtime checks by a factor of up to 10. And this allows us to trade the runtime overhead on executing the program against static verification time. Thank you for your attention.
All right, thank you very much. So as usual, please raise your hand or write on Slack for questions. Maybe let me just start. So this is very impressive, a tenfold reduction in the number of runtime checks. But can you give us a sense how far away that might be from the actual optimum? I mean, do you have like a manually optimized version, and how would that compare?
So the optimization process we applied is actually semi-manual. So we previously defined that we want to try these 2 dimensions. So we tried checking, so the program contains 2 variables, and we tried to just checking one of them or checking the other. And then we did the loop unrolling. So I guess if you apply these techniques, then it's the optimum, or at least the optimum. Yeah, that should be the optimum, because if we try one additional iteration, our approach told us that it's going to fail. And in this case, there is also no dependency on the abstract the control flow we abstracted away. So in this case, it actually should be optimal, but this is only for this one Fibonacci example.
Still very good.
So another program would have control flow, and then we are no longer optimal.
Thanks very much. Joshua.
So I was wondering, you rely on this homomorphism property to do the abstraction, right?
Yeah.
Does one lose much by being forced to use these arithmetic error codes, or are there actually good reasons to use those in the first place? Or could other error codes be somehow more effective?
I'm not sure if other codes would be more effective, but I could imagine that it is possible to adapt these techniques also to other codes, like linear codes. But in this case, it might happen that the operations we can perform our program efficiently would change. For example, with our arithmetic codes, we are not able to do XOR operations using this error homomorphism. And if we instead would use linear code, then we could do XOR operations, but probably might lose other ones. So yes, it might be a trade-off that might be worthwhile to investigate, but we haven't done so yet.
Okay, thanks.
All right. So Joshua is actually also our next speaker. So Joshua Schneider from ETH Zurich, and this is about scalable online monitoring of distributed systems.
Hello everyone, my name is Joshua Schneider, and I will present our approach to the scalable online monitoring of distributed systems. This is joint work with David Basin, our student Mathieu Graham, and Sojourn Christich. Let me begin with a brief overview of the setting which we are working in. We consider monitoring rather abstractly, has the task of checking an event stream against a formal specification. Specifically, we look at online monitors, which really process a stream as opposed to accessing stored files. The events in the stream may carry data. Therefore, the specifications are in general first order. Concretely, we use metric first order temporal logic, MFOTL, as the specification language. The output of the monitor is represented as a vertex stream on the slide, because we want to check the specification at every position. So far, this is all very standard. In the work that I'm going to present, we have been looking specifically into parallel monitors that process multiple event streams simultaneously. Now you may ask, why is this a relevant or interesting problem? Well, the application we have in mind is monitoring distributed systems. Distributed systems consist of independent components that communicate only by passing messages to each other. And the goal of monitoring such systems is to analyze their global behavior. This results in many challenges that have been addressed by the RB community. For example, events are generated concurrently in many locations. They may be propagated with delays, and so on. The motivation for our paper is that distributed architectures are often chosen because they offer horizontal scalability. That means their computing power can be increased by adding more components. But then, also more events are generated, and therefore our monitors must scale too. For this reason, we developed a monitor which processes event streams from multiple sources in parallel. It extends our previous parallel monitor, which offers state-of-the-art parallelization but suffers from the restriction to a single source. Our approach can be used to monitor centralized MFOTL specifications of distributed systems. With centralized, I mean that there is a single specification which can refer to events anywhere in the distributed system. Centralized specifications decouple the system's behavior from its distributed architecture, and we believe that this simplifies the description of global properties. In the paper, we give a formal model called partition temporal structure for the input to multi-source monitors. This model allows us to precisely define what we require of the event streams, in particular with respect to the event ordering. We cannot really avoid having some notion of global clock, but we show that a low resolution is often sufficient. This results in a weaker assumption than the usual global clock. We also proved the correctness of our monitor on an abstract level. Finally, we confirmed experimentally that having multiple sources improves the performance, even when monitoring centralized systems. So let me briefly recap how the previous parallel monitor works. As it is an online monitor, you should interpret the diagram on the slide as a cascade of stream transformation. The input on the left is a single event stream, usually modeled as a temporal structure. These are unbounded sequences of timestamps, databases, which you can think of as finite sets of simultaneous events. The slicer takes the event stream and distributes it to the sub-monitors. These are independent instances of some non-parallel monitoring tool. And for MFOTL specifications, we usually employ Montpellier. Note that some events may be duplicated or sent to multiple sub-monitors. The output of the sub-monitors, that is, the violations they find, are sent to a merger. It just collects all the violations into a single stream. In principle, we could use this parallel monitor also for distributed systems, right? Well, suppose for the moment that all the events are totally ordered, and therefore we know exactly in which order they must be fed into the monitor. So what is the problem then? Well, we see that all events must pass through the slicer. And if the monitored system is large, the sheer number of events might totally overwhelm the slicer. Remember that we are in the online setting. The non-parallel slicer is therefore clearly a bottleneck of this approach. However, an important property of the slicer is that it is a stateless function. Abstractly, you can think of it as a pure function that maps events to a subset of the submonitors. That means that the routing decisions made by the slicer are kind of trivial to parallelize, right? And this leads to the simple improvement over the old monitor that I showed here. We simply run multiple independent copies of the slicer, and each receives a subset of the events generated by the monitored system. This also helps with scalability because we can easily add new slices and streams to feed them. Yet there are two problems with this proposed solution. First, most monitoring tools, including Monitoring, which we run as a sub-monitor, expect their input to be sorted according to the event's natural ordering. If there's no synchronization between the slices, the events may arrive in an unpredictable order at the sub-monitors. We really want to avoid event-by-event synchronization because that would defeat any performance gains from the increased parallelism. The second problem is somewhat related, but also more fundamental. How do we interpret a centralized specification if we do not have a precise temporal relationship between events? Distributed systems avoid full synchronization for the same reason that I just mentioned. As a result, it is often unclear in which order the events from different components actually occurred. To address the first problem, we changed the high-level structure of our multi-source monitor. We indeed run independent instances of the slicer, each taking a separate event stream, which we call a source. For the correctness of the monitor, it does not matter how the sources are connected to the monitored system. And for maximal performance, obviously the events should be distributed roughly evenly. And the important thing is that we added a reordering step to the data flow. The reorderer buffers and sorts the events before they are handed over to the submonitors. This reordering needs additional information to do the reordering, which we assume is provided by the sources. We model the collection of sources as what we call a partition temporal structure, or PTS for short. Such a structure consists of a sequence for every source with index k, where the sequence extends the usual temporal structure with an index alpha and a watermark omega. The slicers simply forward the indices and watermarks. I will only give some intuition about the meaning of indices and watermarks in the presentation. You can find the exact conditions that they must satisfy in the paper. To give this intuition, let's start with a rather restrictive use case, where we actually monitor a centralized system. Why do we even consider this? It turns out that having multiple slices can improve performance also in this setting. We only need to partition the stream first, for example, using a round-robin scheme. And because we are in control of the partitioning, we can add a sequence number to the events and use the sequence number as the index of the PTS. The index then allows us to reconstruct the original order inside of the monitor. And it is obvious how to interpret the specification against the events. Now let's look at the second scenario. If there are multiple independent components to monitor, that is an actual distributed system, we can map each of them to a source. We assume that every component generates its own events in order, but between different sources, we only have a partial order. Since we work with metric specifications, there must be some kind of. Based on what co-authors have shown in previous work, that the partial order described by the timestamps is enough to monitor some, but not all specifications. If this is the case, we set the index equal to the timestamp, such that events with the same index and its timestamp are collapsed. We generalize this idea to a specification-dependent clock model called low-resolution clock, and this I will explain on the next slide. And finally, what we could also do is send the events from a number of components into a single source. This is somewhat similar to the previous case, except that now even the events at a single source may be unordered. And here we require that the monitored system provides so-called watermarks, which are a well-known technique in stream processing. Basically, watermarks provide a lower bound on future timestamps, and that allows the monitor to eventually make progress. So what we have seen is that indices encode the order of events. And it is important to realize that indices coming from different sources have to be consistent. This requires the system to have access to an accurate global clock. A clock is accurate if it tracks reference time, for example UTC, within a small bound. It's denoted by B on the slide. The global clock is an abstraction over a set of local clocks. Each of the local clocks has to be accurate within a small bound for the global clock to be accurate. In practice, one realizes this by mutually synchronizing the local clocks with some time protocol, like NTP. Typically, the global clock assumption implies a total order. But now consider specification, like the authorization must happen at least 1 second before. The 1 second before part is important here. Then it's enough to know that the event time happens in 1 second increments. And it is enough to have a low resolution clock. Such a clock induces the smallest partial order required to check the centralized specification. And the specification in turn determines the clock resolution. So in this example, we only need 1 second increments. We implemented and evaluated our monitor to verify that multiple slices indeed increase performance. Here I'm only showing one out of several experiments. The plot on the left shows the results for the old parallel monitor, which only has a single source and slicer. The measurement on the y-axis is the maximum processing latency. The x-axis shows how much we accelerated the event stream, which directly corresponds to the event rate. The goal is to have low latency for as large event rates as possible. Note that with only one source, we quickly hit the bottleneck. With 16 submonitors, that's the red line, the latency is actually higher than with 4 submonitors, the blue line. That's clearly undesirable. Now on the right, you can see the results for the same data, but now with 4 sources, and therefore also 4 slices. The black line, where we only have 1 submonitor, is more or less the same, as is expected. Now we can unlock the scaling potential of adding more submonitors. You see that the latencies for 4 and 16 submonitors are indeed much lower. Before I conclude the talk, I want to point out some differences to related work. Here I'll focus on a selection of works that target the monitoring of distributed systems. The decentralized LTL monitoring by Bauer and Falcone, and also the Tennis tool provide parallel monitoring. However, both are limited to propositional traces and specifications. The propositions there must be associated with unique components, so it is not possible to have truly centralized specifications. Then there's also the stream RV tools, Lola and Tesla, which are first order in the sense that they support events with data. Tesla has a parallel implementation based in the L1 ecosystem. Neither Lola 2.0 nor Tesla support centralized specifications that abstract over the mechanism of event delivery. What we call sources must be modeled explicitly in the languages. Our parallel monitor is also first order, but it can handle centralized specifications. I want to point out that there are monitoring algorithms which can take unordered event streams as inputs. And those could actually be used as submonitors within our approach, and that would render the reordering step superfluous. Evaluating this particular combination is future work. So, to summarize my talk, we looked at the problems that arise when we want to monitor distributed systems online and in a scalable manner. Specifically, a single event stream is not enough. Therefore, our new parallel monitor reads events from multiple sources and uses slicing to achieve parallelism. Because of the independent source streams, some reordering is necessary, and the sources must provide additional information for the reordering step. This additional information can be summarized as a low-resolution global clock, whose resolution depends on the specification to monitor. With our evaluation, we can confirm that increasing the number of sources improves the scalability of the slicing approach. So, thank you for your attention, and go ahead with your questions.
Thank you very much. So we have time for questions. Joshua, I really liked your diagram with the related work bubbles. I was wondering, is my impression correct that your approach is not really specific to mThotal, and one could more or less do the same thing for a loader specification, for example?
So yes, the slicing part in principle should work for any specification language that has that supports events with parameters. One has to look a bit into the specifics, how it would be implemented, but it should work. And then the sub-monitor could just be any monitor algorithm for that language. So as long as the model that we use to represent these streams is somehow compatible with that language, yeah, I would agree. So this should be possible. We just focus on mThotal for concreteness because we have the tools for that, and the examples work with it.
Yeah, but I think that is definitely something people should look at because it's such a useful formalism. So Zoom orders the request. So let's start with Roderick.
Yeah, thank you. So I was wondering what kind of properties you see in practice, and then if you split them into monitors, what kind of structure you get, whether you have a bunch of monitors that each just look at one server, or whether they pair such servers, and whether you can do something with that.
Right. So in our approach, what we do is we don't look at the structure of the specification directly. It's more the data that is associated with the events that influences how the events are distributed between the monitors. And then one could either, craft a specific scheme that's fine-tuned for a concrete system. But what we usually do is just use randomized approaches where you have like a hash function that is applied to the data, and then this kind of ensures that the data is distributed evenly. So it should be, to a certain extent, independent of the structure of the system.
Thank you.
Right. Thanks. Oleg.
Thanks. Great talk. My question is, so you said that the resolution of the clock you need depends on the specification, and that makes sense, but I didn't quite get what the dependency is. Is it easy to figure out, look at the specification and figure out, hey, I need this much resolution?
Yes, more or less. So the logics that we use, we consider discrete time semantics. So your timestamps are already assumed to be in a certain unit. And often this is not something you see directly in the specification, but it's reflected in how you encode the events. But once you have this information, you already have the granularity of the clock because it's directly related to the semantics.
So wait, what I heard you just say is that it really depends on the property of the source and not so much on the specification. The granularity of timestamps.
It's related because in the specification, you just have these time units, right? And you need to know what these mean in order for the specification to make sense, to reflect what you actually want to specify with the formalization of the property. And this is related to how you generate the events, right? Just as in the same way as you have to give names to the events that occur in the system, right? There's also an implicit contract between the names that you use in the specification and what you use in the source of the events. And the same, it's for the time unit.
Sounds good. Makes sense. Thank you very much.
Thank you.
Right. One quick final question by Thomas.
Hello. I really enjoyed your talk. I was just wondering, in your talk, you mostly focused on performance of monitoring. Have you thought whether this distribution can apply to redundancy, say if one of the sub-monitors fails or takes much longer than the others to return result?
Yeah, that's an interesting idea. So we haven't really thought about this. One exception being that we have an extension of the slicing approach where we try to figure out when we need to change the slicing scheme dynamically by actually observing the processing latencies in the submonitor. So that might be a bit related. That was an ADVA paper from last year where we described this. But yeah, the redundancy idea, that sounds interesting, and we haven't thought about this.
Thank you very much.
Thank you.
Thanks very much, Joshua. Now, our final talk of this session is on test for enforcers, and the speaker is Oliviero Riganelli from the University of Milano Bicocca.
Hi everybody, I'm Oliviero Riganelli and I come from the University of Milano Bicocca. Today I'm going to talk about test for enforcers, that is a new technique to automatically generate test cases that can be used to validate enforcer implementations. This is a joint work with Michel Guzman, Daniela Micucci and Leonardo Mariani. In several domains such as mobile and web, runtime enforcement techniques have been successfully applied in order to ensure correct program behavior. The correct behavior is specified in policies that may cover several aspects of a program's runtime behavior, such as resource management or security aspects. In this slide, I have reported a policy regarding the use of the camera resource in Android devices. This policy says that the camera must be released as soon as the app is paused. If the app doesn't release the camera correctly, all subsequent attempts to access the camera will fail and may cause the app itself or other apps to crash. In the runtime enforcement schema, we have an enforcer component that captures the interaction between an untrusted app and the system. And when a policy violation is detected, the enforcer corrects the app execution, for example, in this case, by releasing the camera before pausing the app. How to correct a wrong execution is specified in an enforcement model. There are several models in literature that can be used to express an enforcement strategy, such as edit automata or input-output automata. Here I have reported an input-output automaton that shows how to enforce the camera release policy. The inputs are the requests intercepted at runtime by the enforcer, and the output are the API calls performed by the enforcer in response to the intercepted requests. When we are in state 0, the camera has not yet been acquired, and the unpause can be executed without changing the behavior of the app. If the camera is acquired by executing open, we move from state 0 to state 1. If from state 1 the camera is released, then we move back to state 0. But if from state 1 the app is paused, then the enforcer corrects the behavior of the app by forcing the release of the camera before pausing the app in order to avoid the violation of the policy. As you can see here, the enforcer changes the execution of the app when the output is different from the input in terms of required and executed actions. The enforcement model is then used to guide the implementation of the enforcer software that can be obtained through a manual or automatic code instrumentation. With the code instrumentation, the app code is modified to insert the statement necessary to monitor and change at runtime the behavior of the app according to the enforcement strategy specified in the model. But the actual implementation of enforcer may exhibit unexpected behaviors due to three main issues. The first one is inaccurate enforcement models. Even if the model seems to be correct, the enforcement strategy may end up being wrong. For example, an alternative enforcement model for the camera release policy could, in case of policy violation, suppress the on-pause invocation instead of forcing the camera release. By doing so, the policy is not violated, but the strategy is inaccurate because the system will hang. The second issue is the inconsistent enforcer implementations. The enforcement model must be translated into working code, and sometimes, especially when the code generation is completely or partially manual, the implemented behavior may differ slightly from the model one. The last issue is faulty enforcer code. Enforcement model may be difficult to implement because they may require a strong effort of adaptation and instrumentation, resulting from the gap between the abstraction used in the model and the actual behavior of software. And this could lead to software bugs that can result in runtime failures or errors. Starting from the enforcement model, the goal of Test for Enforcers is to address these issues by automatically generating test cases that can be used to validate the enforcer implementations. Test for Enforcers generates these test cases in three main steps. The first two steps that can be performed in parallel are generation of test sequences and GUI ripping with monitoring. The first generates the test sequences that must be covered in order to truly test the behavior of the enforcer based on the behavior specified in the enforcement model. The second step, GUI ripping with monitoring, explores the user interface of the app under test in order to identify which user interface events cause the execution of the operation that are in the enforcement model. The output of this step is the Test for Enforcers model, which is a finite state model that represents the GUI states that have been executed, the GUI events that cause a transition between states, and the operation belonging to the alphabet of the enforcement model that are triggered by the events. Finally, the third step, the concrete test case generation, looks for path of GUI events in the Test for Enforcer model that exactly cover the test sequences identified in the first step. These GUI events, enriched with program oracles, are the test cases that can be executed to validate the actual enforcer behavior. Now, let's take a closer look at these three main steps. The test sequence generation step generates the sequences of operation that must be covered by tests to determine if an implementation is correct with respect to its specification. There are several methods to derive test sequences from finite state machines. Test for Enforcer uses the harmonized state identifiers method, which generates input sequences to reach each state of the model, cover all transition from each state, and identify all target states to ensure that their counterparts in the implementation are correct. Applying the HSI method to the enforcement model for the camera release policy, we obtain the 5 test sequences that are shown here. The goal of Test for Enforcers is now to find GUI level test cases that are able to exercise these 5 test sequences. For this reason, in the second step, a model of the GUI of the app under test is built. GUI ripping generates the state-based model of the application under test by systematically executing every possible action enabled in the GUI until a given time budget expires. The actions that can be performed are GUI events such as touching a button or typing a text in a text field, and so on. During the GUI ripping process, Test for Enforcers also monitor the execution of the operations that are in the alphabet of the enforcement model, because we are interested in identifying which events in the GUI cause the execution of the operations that are in the test sequences. The generated model is a directed graph where Each node in the graph represents a GUI state that is defined by the element called views that make up the GUI. And each edge between two nodes represents a test input called event that triggers the state transitions. An event is defined by the type of GUI action, such as touch, the view on which the action is performed, the ADB command used to execute the event on the device, and the operations in the enforcement model that are triggered by the events. The last step is the concrete test case generation. That consists in finding a sequence of GUI events that cause the execution of the operations that are in the test sequence. The GUI events that cover the test sequence are identified in the test for enforcer model by applying a path search algorithm. In this example, test for enforcers identify a path from the initial state that cover the test sequence open, release, on pause. How you can see, the open is executed by the second touch event allow, and both release and on pause are executed by key event home, which is the last event of the path. Finally, to verify the correctness of the enforcer, test for enforcers adds differential oracles to the test. The differential oracle determines if an enforcer behaves correctly by comparing the execution of the test with and without enforcer. Test for enforcers can add two types of differential oracles, the transparent enforcement oracle and the actual enforcement oracle. The transparent enforcement oracle is applied when the enforcer does not modify the app execution, and therefore we expect the outputs produced by the test with and without the enforcer are the same. The actual enforcement oracle is instead applied when the enforcer is expected to modify the execution of the app. And this time, the outputs produced by the test with and without the enforcer should be different. In the early evaluation, we applied test for enforcer to the camera release policy enforcer and tested its behavior with the FUCAM app. That is a real camera app that can take multiple shots with different exposure settings. For the evaluation, we consider two implementations of the FUCAM app, one that violates the policy and one that doesn't violate it. In this experiment, we have measured the size of the enforcement model and the number of covered test sequences. We ran the experiment on a device with Android 8, and we executed the GUI ripping process for 30 minutes. In both versions of the app, the GUI ripping process produced a model of about 60 states and almost 300 transitions. The small difference in the number of states and transitions is due to the crashes caused by not releasing the camera in the faulty version. Obviously, the size of the model depends on the complexity of the app used for the test. And FUCAM is a real but relatively simple app. This table summarizes the results on the feasibility of covering the test sequences in both versions of the app. The app column indicates the app that is tested. The test sequences column indicates specific sequences of operation that must be covered by test cases. The coverage column reports if a test case covering that sequence has been found. And analyzing the app code, we found that many test sequences are infeasible, which is why test for enforcers was unable to find a test case for these sequences. For example, every time you open the FUCAM app, the camera is acquired by executing the open operation. So it's not possible to cover test sequences that do not start with the open operation. Anyway, Test for Enforcers found test cases that cover all the feasible test sequences. The execution of these concrete test cases with and without enforcers confirmed the correctness of the enforcer for the FUCAM app. The runtime enforcement is a useful technique that can be used to ensure that certain policies are met while an untrusted app is running. However, specifying enforcement strategies and implementing the corresponding software could be a challenging task. For this reason, the actual implementation of enforcers may exhibit unexpected behaviors. And to address this problem, we have developed Test for Enforcers that is able to generate test cases for validating enforcer implementation. The early evaluation showed that Test for Enforcers was able to generate test cases based on the implementation of the application under test, and that these test cases were useful to validate the implementation of the enforcer and cover the most relevant test sequences in the enforcement model. But this is a small experimentation to evaluate the feasibility of the approach. In the future, we plan to perform a more comprehensive evaluation. Thank you for your attention.
All right, thanks very much. So there's a question by Elias.
Yes, thanks, Bern. Very nice work, Oliviero. I was wondering how you perform instrumentation, and my understanding was that you needed maybe to handle resources in the underlying program. I think you have some kind of Android context here, and if so, how do you handle this? Thank you.
If I understand, you asked me how I perform the instrumentation to collect the events in the enforcement model. Yes, I didn't present here a step that is the monitor generation. We generate the monitor using Expose, that is a framework to instrument the application when it's loaded in the in memory. And we have a schema of the monitor, and for the input for the generation of the monitor is just the method that we want to monitor their execution. But we are working on Test for Enforcers, and in the new version we also use the trace analyzer provided by Android Studio in order to get the events that are in the model.
Okay, very nice. Thank you.
Benedict?
Yeah, thank you for your talk. It was very nice. Oh, it must become dark outside. I have a question about the events that you're using. How complex events can you do? So you had this enable camera or disable camera. Is it also possible to have parameterized events? Or
yeah, sure.
So
yeah,
like,
yeah, sure.
You're not allowed to access a certain folder if you're not authorized to do so. Could you possibly express something like this? But you are allowed to express a different folder.
Okay. We in this work we just use Test for Enforcers in the Android environment, and what we can monitor is every API that are in the framework, and so and so we just can monitor every method that are in the API of Android.
Okay. Thank you.
Yeah, and so, but we cannot monitor, for example, the file system of the devices.
Okay, but you can monitor different functions if they are in this API specification.
Yeah. Yes. Right.
Yeah. Thank you very much.
Thank you.
All right. Thomas, I see that your hand is raised, but I'm not sure if that's for this talk or still for the previous one. I'm guessing it's for the previous one then. Well, if there are no further questions, then thank you, everyone. This was a great session. And we now have a 8-minute break till the session on RV for software systems. See you then.
And
Thank you.
just to remind you, there's an RV Tavern Zoom room where you can go out, pretend that we are all virtually drinking coffee or something, and get back to the next session at 9:40. Okay, thanks, Bernd. Very nice.
Right.